So now that we have work and we have kinetic energy, we should go to the other type of mechanical energy, which is gravitational potential energy. So just as some definitions here, mechanical energy is the sum of an object's kinetic and potential energy. So you just add those two values together, whatever they are, that's mechanical energy. Potential energy, just in general, is some type of energy that's stored, which can be converted to some other type. Although I don't know any type that can't be converted. Gravitational potential energy, which is the type we'll use mostly in here, is potential energy, so stored energy that an object has because of its position and the force of gravity on the object. To lift an object a distance delta h by applying a force that opposes gravity, and as we know, the force of gravity is just mg. The work done is mgh. So hopefully that's mostly a review. We had that equation last year. By the work energy theorem, just a reminder, we just looked at it. Work is just the change in energy. Once again, positive work is work that you do to the object. Negative work would be work that the object ends up doing to you. And so the change in gravitational potential energy, if you move an object some distance, right? If you pick an object up and move it to some height opposing gravity, then that's the change in gravitational potential energy. So we can just basically replace work there and say that. Again, the units are joules. And a note here, what I think is kind of important, is it's only the change in gravitational potential energy that matters, right? So you can decide, now usually when you're solving problems, you're dealing with changes in gravitational potential energy. As with any coordinate system we've used so far, it's up to you where you want to define h equals 0, right? If you've got something happening on a bridge, you can say, well, the water below is 0. Or you can say the bridge is 0, right? Whatever helps you solve it or get to the answer more quickly. And at the end, everything should work out because it's really just the change in gravitational potential energy that matters. That brings us now to the law, so you know it's important, of conservation of energy. And this just says that energy cannot be created or destroyed. It can only be converted from one form to another. So a really interesting thing that we get this quantity, if you will. We define the unit as joules, so like, you know, the force times some distance. And if you look at it even more generally, like a joule, like a kilogram meter per second square, meter squared per second squared, like this thing works out to be this really universal quantity that's conserved in any sort of interaction between, you know, particles of any type or systems at large. This seems to be the, you know, most significant quantity that we can say, no, this is conserved, this quantity somehow, right? So very kind of important law of nature, if you will. Just to be very clear, I mentioned them before, but open and closed systems. So when isolated or closed, and I'll probably use those terms interchangeably. This is a system such as our universe. I put that little bit there because who knows, maybe our universe turns out to be an open system. It cannot interact with any other system, right? So the total energy remains the same, right? Just changes from one type to another, right? Whereas an open system, so look at something like a refrigerator, the system can interact and exchange energy with its environment, right? i.e. with other systems. Thus, within an open system, the total energy need not remain constant, right? It can actually release energy into the environment around it, or it can get energy from the environment around it. And there's some kind of little diagram of it, right? An open system, it's interacting with its environment, exchanging energy, whereas a closed system, you're looking at it like an isolated thing, even if it's just for, you know, solving a problem, right? And you're just saying, well, I'm going to look at this as a closed system. There might actually be some in a real situation. Like I said, even if you try to isolate a box or something, well, it's probably going to radiate and all that, so you're going to have issues, but we'll look at it that way. Finally, power is the rate at which work is done by a force or the rate at which energy of an open system changes. So we just define work or power as, so in this case, the W here would be work. And if you also remember the work energy theorem, you could also write this as delta E over T, where T, you could even say delta T, right? Whatever time interval this is over. So to look at a fun example, excited about the law of conservation of energy, a student jumps a dirt bike off a ramp. The end of the ramp is 30 meters above the ground, right? So that's telling you here at this point, this would be 30 meters. And we'll just assume the ground is somewhere about here. And the student's speed at the end of the ramp is 40 meters per second, right? So I'll just sort of draw that. Something like this. So we'll say V1 equals. Note this is speed, not a velocity. And we'll assume some sort of path where it comes up and reaches some maximum height and then comes down. And what we want to know is V2 when this person hits the ground, right? So this might seem, especially after doing a dynamics unit, like, okay, we could break this V1 up into V1x and V1y. We could look at gravity in the y direction and then figure out, the components of V2. And we could do all that. Absolutely. You could solve it that way. But this is where, energy is just so much more helpful because it's all built right into those equations. We only need the speed with which this thing hits the ground, right? Which is to say we need the magnitude of the velocity when it hits the ground. We don't need the components of it or the direction, like relative to the horizontal. So using energy equations, like I said, everything is built right into that. We can just get the speed right from that. So the real key here, right, is that energy equals constant, right? E total equals constant, right? It doesn't change. So we can look at, now I would define at this point here, we'll say that when it hits the ground, we'll say H equals 0 here, right? So that means we'll just say at point 1, which is at the top of the ramp, there's some kinetic energy, some gravitational potential energy, and then when the person hits the ground, there's some kinetic energy, and we'll say no gravitational potential energy because we'll define H equals 0 at that point. Right? So in other words, EG1 plus EK at position 1 equals EG2 plus EK2. And we can put in the numbers here. EG is just mgh plus 1/2 mv1 squared equals mgh. I guess here I should say h1 and h2 plus 1/2 mv2 squared. Now, there's a mass in every one of these terms, and I don't think I'm even given a mass, but that's fine because they all cancel out, right? There's a mass in every term, so we don't even need that. And putting in a few numbers here then, GH1, G is 9.8. We said that H1 was 30 plus 1/2 times 40 squared equals 9.8 times h2, which we said is 0, so this whole thing will just cancel, equals 1/2 times v2 squared. So yeah, there's a question here about my use of 9.8, and it's not negative. Remember, these are all scalar quantities, right? So yeah, gravity's acting in the negative down direction, but we're defining the gravitational potential energies that something has is just mg. G is just 9.8 in that, times whatever the height is, right? So if you only looked at gravitational potential energy, right, you would say we're defining the height to be 0 here. So that means EG here would be 0. And we want this person to have gravitational potential energy when they get to this, height up here. So that means we just leave it as 9.8 times whatever the mass is times positive 30 because we've gone up. So when you're doing calculations with gravitational potential energy, keep 9.8 positive. It's only the height that you're going to list as potentially negative, right? If I had said this height here is 0, then I would have to say when this person hits the ground, they're at negative 30, and then that negative 30 would go into my equation. So yeah, now I can just work out the numbers here. That means I've got 294 plus, 40 squared would be 1600. A half of that would be 800 equals 0 times 1/2 v squared. Multiply both sides of this equation by 2 so that cancels out. That gives me 1094 times 2, which is 2188. Oh, I stopped putting the subscript 2 there. And so then I just take the square root of both sides and I get V2 equals 46.8. And again, that's just a speed, but that's really all I want. I don't need the individual components. And so you can see just how much work, no pun intended, how much work that saved me not having to go through the whole process in dynamics and look at each dimension independently and all that. I have what I actually want. Okay, one extra little bit here. To perform this stunt, the dirt bike was accelerated from rest on the ground to 40 meters a second at the end of the ramp in 5 seconds. If the mass of the dirt bike and student is 400 kilograms, how much horsepower was required? We'll assume that this was sort of administered at a constant rate or whatever. And so, in other words, we're saying at some point, I guess back, well, maybe even farther, but way back over here, just to get to this point, right, this dirt bike had to accelerate 400 kilograms to this height and to this speed, right? So first then, let me actually figure out what the total delta E was, right? What the actual change in energy was. So we'll assume that, again, that same height of 0. So that means initially E1, right, we'll just say was 0. And so delta E really is just going to equal E at top of ramp. Right? Which at the top of the ramp, I'm really just looking at mgh plus 1/2 mv squared. And I'm now told that this is 400 times 9.8 times a height of 30 plus 1/2 times the mass of 400 times V2 was 40 squared. And if I put in the numbers for that, I get 437,600 joules. It's a lot of joules. And so that means the power, which is, in this case, delta E over T, would just equal 437,600 over the time that this took place, which we're told is 5 seconds. So we can divide that by 5, and that gives me 87,520 watts. Right? Now we're asked how much horsepower was required. Well, horsepower is a unit of power, and we're actually given the conversion here. Note that 1 horsepower equals 0.7457 kilowatts. Right? I've got my answer in watts, so to get that in kilowatts, I just divide it by 1,000. So that would equal 87.52 kilowatts. Then I can actually use that conversion factor, which is just to say I can multiply that number by 0.457. 7,457. This would be horsepower per kilowatt. So I know, like, just even looking at the units, I see kilowatts are going to cancel out. And that will leave me with 65.3 horsepower. Sorry, my brain wasn't working there. If you take this conversion here, I don't know, sometimes it just takes me a second. So one thing what helped me catch this mistake, and it's an important mistake, is that when I look at this, I'm saying, well, if you have some unit of horsepower, the kilowatt unit or the amount you have in kilowatts should be less, right? If you got 1 horsepower, you've only got like roughly 0.75 kilowatts, right? It should be, so when you convert to horsepower, the number should be greater. So if I actually take these numbers and divide, right, that means 1 kilowatt equals 1 divided by 0.745. Which is 1.341 horsepower. And that's the number I actually should have used here. And if I multiply that by 87.52, I get 117.4. A little more than I had thought. So just a lifetime silly mistake. Sorry about that. Okay, so for this simulation, and let me reset it, right? You can see, if you're watching the speed of the car, you can see it gains speed as it goes down. And in this case, it breaks the egg. I think you reduce the hill or whatever. I'll leave the hill constant. Now, first question is, what happens if I change the vehicle, right? We can see that I got a speed of, well, basically 400 centimeters a second, 401.1. But what happens if I reset this? And let's go all the way to the big one. What if I go to this? Now we've got a 100-gram little toy car that we're going to let fall down this ramp. What should the final speed? Should the final speed be greater or less? Right? I can understand why a lot of people would think greater. It's a more massive object. It's probably consistent with their everyday experience. This should go all the way back to dynamics, though, when we looked at g equals 9.8 and why all objects accelerate at 9.8 meters per second squared, right? And I'll play it just so you can see they made a good sim. There we go, right? Exact same speed. Remember, more massive objects have more inertia, right? So it takes more force to accelerate them, but also the force of gravity on them is stronger, right? Because the force of gravity is proportional to the mass. So those two balance each other out. It travels at the same speed, doesn't matter what car we use. But where this gets interesting is I can put a little hill in the middle let's go, I like 50. There's a nice number. So now we've got a hill. So the car is going to go down, and then it's going to go over this hill and then hit the egg. Now, all I want to know is the final speed when it hits the egg, assuming it gets over this hill and hits the egg. It should. I turn friction off. What's the speed going to be when it hits the egg now? Is it going to be still 400? Is it going to be greater than 400? Is it going to be less than 400? What do you think? Okay, well, let's see. It's a sim. Here we go. And down and up and down and... What's the final speed? It's the same, right? And that's because, right, remember the conservation of energy. So as whatever the energy is, and we're only dealing with mechanical energy here, no matter where on this, graph you look, the total energy is the same, right? All that's happening as the car moves down the hill and then up the hill is energy is being converted, right? From gravitational potential energy to kinetic energy, or from kinetic energy when it's going up the hill, it's just converting some of that kinetic energy back into potential energy. But then when it gets down at the bottom, right, all of that energy is kinetic energy again, right? So all you're ever doing is exchanging one for the other. The total remains the same. So anytime it's at that height, which is, let's call that 0 at the bottom, the speed should be 401.1. It should be constant. Okay, I got one more for you. So this I took, this is someone else's video. I linked it on the course plan. He set up this track here, and you can see they're basic these, and he's got two metal balls in his hands, in each hand, and he's going to send them at the same time. He's going to release them, and they're going to go on these two separate tracks, right? Both tracks offer basically zero resistance or whatever, right? One is going to go down a little bit and then straight across. The other one is going to go down and then down some more. The question is, let's say there's the track closest to us, right, where it goes down, and the track farther from us. Which ball will reach the end first? And if you're thinking about energy, right, they both have the same energy the whole time, right? I can understand that thought. Let's have a look. I think this is going to happen quick as soon as I hit play. So here we go. There you go. Here, I'll even try to go back. Oh, here's going to show you in slow motion. So which one reaches the track, the end of the track first? Yeah, it's the one that goes down lower, the one closer to us. And the reason is, yes, they both have the same energy the entire time. That's non-negotiable. But, right, what happens to the one closer to us is when it goes down lower, it exchanges some of that kinetic energy, or that potential energy, for kinetic energy. And so it moves faster while it's at that lower height. Then it goes back up to the same height as the other one, which means it also goes back to the same speed as the other one. But it got to go at that lower height for a period of time that the one farther from us didn't. So it ends up getting to that final spot sooner.